That's recording.
Anyway, okay, so how many did the pre-lecture reading? Yeah, not everybody, but it's pretty short, right? In fact, you're excited because of the pre-lecture reading, right? You're like, that sounds really cool. I want to go and learn about that.
This is only the third time somebody's promised they'll teach me group theory. I just hope you actually do it.
Okay, yeah. So I make no promises. All right. So the website's been updated with my office hours. Zach's also going to hold some office hours, and once I get a room from him, I'm going to update it with his office hours as well. I'm going to try and go as long as I can before my throat gives out. But generally speaking, excuse me. I've got 2 hours on Monday night because I know many of you might be working on your homework then because it's going to be due Tuesday. And I think Zach's going to have some earlier on Tuesday so you can get some help from him. Anyway, all right. So we're going to get started. And are there any outstanding questions from last time we met? By the way, I did not get through all of my notes from last time, but I did post them all. So at some point it might be worthwhile to go back and look at the notes that I posted on the course website just to see. There was one little bit at the end that I didn't get to. Okay, so I was thinking about today, and I was going to reorder some things, but then I thought, no, I'll keep it in the order it's in, and then just kind of talk around it. But there's one of the things you'll realize as you get further on into physics is that there are some things that you've been doing all along that's never really been named or given like a formal name and a formal explanation. And a lot of that is because making it formal almost like makes it too intimidating. It's easier to just work through or work with the very examples as you encounter them. But then every now and then you get to a course where the ideas that have not been named either become so important or they're so pervasive throughout a particular course that you just have to go ahead and name it. Okay, so the ideas involved in group theory are something that you have been working with since you were taking your very first math class, believe it or not. You were toying around with the elements of groups when you first learned arithmetic. But you've been able to get a long way in math without having to really formalize it. But this course, it's going to be so important and pervasive in this course that we might as well just go ahead and formalize it. And so for those of you who have not seen it before, today will be your first introduction to group theory. For those of you who have seen it before, hopefully this is old hat. So to sort of motivate, we'll get to group theory in just a minute, but to sort of motivate it, one of the themes of this course is going to be the notion of symmetry. And symmetry in physics has a lot of important aspects. One, which you're probably most familiar with, is the idea that if a problem has symmetry, or if you can recognize symmetry in a problem, then often it makes the problem easier to solve. Right? So everybody knows you would rather study a spherical cow than a real cow for reasons of symmetry. And so that's sort of the utility of symmetry. And that's kind of cool, and many of you probably want to go out and do some real honest physics, like solving problems. But then there's the people who care about the important stuff, like me. No, I'm just kidding. No, there's actually a very deep role played by symmetry in physics, which we're going to uncover in this course in a manner that you might not have seen in your other courses, and that is that statements about symmetry actually underlie the fundamental interactions in the universe. Okay, so if we cut through all the crap and we get away from effective forces like friction and normal force and all that, and we just talk about the fundamental forces, all of the fundamental forces as we understand them are really statements about symmetries. Okay, so symmetry actually plays a very deep role, and what we would like to do is study symmetry in its various aspects in this course. But before we can study symmetry, we actually have to study something which is a little more primitive. And what I mean by that is the idea of a symmetry. Well, actually, somebody just throw out, what's your idea of a symmetry? What do you think the word means, symmetry? An invariance under? Right, exactly. So the notion of symmetry is that you do something, you have a transformation, and then you have something which is not changed, or its appearance is not changed under that transformation. So in truth, before we can dig into the guts of symmetries, we really need to take a step back and talk about transformations. And it's in the language, or it's in the formal description of transformations that we're going to find the language of group theory to be useful. Now, there's a lot of words that come into play when we describe and talk about different transformations, and a lot of them are going to be relevant in this course in different contexts. So I'm going to go ahead and throw a lot of those words out to you with examples to clarify it. And I have to say that today's lecture is going to be really nice, because I feel like there's not a single thing I'm going to say that I'm not going to use words that you haven't seen before. I'm not going to use ideas that you haven't seen before. I'm really just going to formalize a lot of things that you are already pretty comfortable with. Now that's a double-edged sword, right? Because it means it's easy for you to grasp what I'm saying, but it's also very difficult for you to grasp what I'm saying, because you already think you understand what I'm talking about, because I'm going to say and talk about concepts that you're already familiar with. But you have to kind of let yourself back up and say, okay, there's a reason why he's talking about something that seems incredibly obvious. And that's what a lot of hard math is really about. It's taking something that you're already familiar with and abstracting it to something which is more powerful, okay? So first of all, I'm going to use a lot of examples, and it's probably the first kind of symmetry that you ever encountered, of what are called static symmetries. And static symmetries are basically, they're the kind of symmetries that you can see, okay? Because I think when we all think about symmetries, as early as we can remember, we think about, oh, if I look in the mirror, I see something that looks just like me except backwards. So for example, and we'll talk a lot about this example, if I have a triangle, if I hand you an equilateral triangle, then one of the things that you immediately know is if you take that and you keep rotating it by 120 degrees, it always looks the same. Okay? So static symmetries we often associate with geometries, or less technically, the shapes of things. Okay? More relevant for this course, and more generally used in physics, are the notion of dynamical symmetries. And dynamical symmetries are actually symmetries that arise when you consider the evolution of physical processes, the dynamics. Okay? Dynamics are often encoded in different descriptions. In this class, we're gonna lean heavily on Lagrangians. Okay? So writing down a Lagrangian for a physical system is one of several different ways of specifying the content of the physical system. How many of you are familiar with Lagrangian mechanics? And don't be shy if you're not. I am going to give you a little primer on Lagrangian mechanics when we come to that, to where it's needed. But for most of you, I know you saw it in your intermediate mechanics class. In the context of Lagrangian mechanics, when you write down the Lagrangian, which is a function of, for example, generalized positions and generalized velocities, that is writing down the physical content of the system, the degrees of freedom and the interactions between them. And then you couple that to Hamilton's axiom principle, and then that gives you a way to derive the equations of motion which govern the evolution. But don't worry if all that's going, we haven't studied Lagrangians yet, it's okay. But in this context, a symmetry would be a transformation that I do on the Lagrangian that ostensibly changes the Lagrangian, but what I find is that after I do the transformation, the Lagrangian I get after the transformation looks exactly like what I started with. Okay? These are distinct. I mean, this is not something that you put right in front of you and it's like, oh, look, that's a square Lagrangian. You know, that doesn't mean anything. It's going to be like, you know, various fields or or functions multiplied together, and then you're going to have some transformations on those. But at the end of the day, at least the mathematical form that you wrote down to begin with is what you end up with after you do the transformation. So these are the kinds of symmetries that we're going to focus on in this course. But for today, in getting some examples that you can really wrap your head around, I'm going to focus largely on static examples. Okay? So don't think this is a course on triangles, even though at the end of this lecture you might feel, wow, this is a course on triangles. Okay, so, all right. So when you actually look at this thing, your initial inclination might be to say, well, if I were to create something which is invariant, which has a symmetry, then what could you build it out of? So if you want something to be unchanged when you do a transformation, can you build it out of things that do change? Or do you need to build it out of things that don't change?
Build it out of constants.
Well, the very notion of what the word constant means gets a more formal definition in this discussion. Okay, so I think we all have a kind of a back of our mind, I know what a constant is, but even that is going to be something which is going to be given a more formal meaning. But so it would. So let me just answer my own question, which is, it would be uninteresting if, to get a symmetry, you were only allowed to work with objects which themselves were invariant under transformations. That's not very interesting. What's going to be interesting and what we're going to discover is that we can, in fact, work with things that transform so long as we have rules for combining them to create invariant objects. Now, what I just said was hoity-toity, but can somebody give me a very down-to-earth example? Matt?
I don't know if it's super down to earth, but we use DS for invariant in general relativity, where, yeah, the change in time and change in space combine together to create that's invariant. But
Okay.
time and position and that stuff can change.
Okay, you're like so hoity, you're more hoity-toity than me. Congratulations, I'm going to bring a hoity-toity hat next time and let you wear it. Yeah, no. So you want to...
Yeah, the 3 lines on a triangle, they turn, but the triangle doesn't change.
Yeah, so I'm gonna beat on static examples a lot in a minute. It's actually a little bit... It's actually a little harder in static examples, but let me actually just flesh out what Matt said in a more pedestrian language. Vectors. Okay, we're all familiar with the idea that if you take a vector and you break it into components with a coordinate system, and then you rotate the coordinate system, the components of the vector change, right? But can you take a vector and make an invariant out of it? How do you do that?
Take its magnitude.
Yeah, you dot it with itself. You make it a scalar. So you've created something which is invariant, the dot product of a vector with itself, out of something which itself transforms. That is a theme which we're going to lean on heavily in this course. We're going to develop a very mathematically sophisticated idea of a dot product. Okay? All right. So for now, we're going to talk about symmetries much more later on. For today, I just want to focus on transformations and sort of getting a mathematical description of transformations on the table. And then we'll come back to how we actually implement them in Lagrangians and make sure we have symmetries and so forth. So, some more words. So everything that I'm about to say is in regards to transformations. So the first pair of words that I'm going to throw out there is the notion of global versus local transformations. And again, everything that I'm going to talk about, I'm going to try and illustrate with static examples. So here is an example of a system, and then I'm going to do each of these types of transformations on the system. So this is going to be my example 1. So the system under consideration is going to be an array of 9 dots. See, I'm not bringing in any notions that you didn't see in kindergarten. Dots. Everybody's comfortable with dots. Now, I'm going to start with a global transformation of the dots. And my transformation, in this case, is going to be a translation of the dots. I'm literally going to translate the dots in space. Okay? So I could, for example, take all of the dots and just shift them uniformly. And if I do that, I'm going to end up, hopefully with no surprise, with something that looks exactly like what I started with. Because if I take this dot and I translate it to this position, the notion of global means I do the same thing to every other dot. Okay? Now, you might notice that there is a sense in which this global translation is a symmetry of what I started with. Because if I think about what I started with, it looks kind of the same as what I ended with. I mean, yeah, it's moved over, but if all I'm comparing is how these are oriented with respect to each other, it looks the same here that it does there. Okay? I can contrast that with a local version of the same transformation. So this is the same transformation, but now I'm going to do it locally. And what a local transformation means is that I am allowed to implement the transformation differently for different objects. So for example, this guy I might translate to here by a vector like that, but this guy I might translate to by a different vector. And then this one by a different vector, this one by a different vector, and so on, and so on, and so on, and so on. Okay? These are all related to these positions by translations of dots, but I'm using a different translation vector for each and every dot. I am locally allowed to pick my translation. Okay? Now, looking at this example, is there a symmetry under, or an invariance under the local transformation, at least the example I chose?
The number of dots.
Well, no. Okay, yeah, sorry. There are certain aspects of it which are symmetric. I agree. The number of dots, that's a good point. But in terms of thinking of the layout of the dots with respect to each other, is that symmetric under this transformation?
No.
No. Okay. You might in fact ask yourself, how the hell would you ever get something which is symmetric? And let's look at it under this local type transformation, and let's actually just look at an example. So my second example is going to be in terms of a system that is comprised of 4 circles. Okay? And once again, I'm going to consider both a global version and a local version of a transformation on this system, where the transformation I have in mind is going to be a rotation of each circle about its own center. Okay? So for example, I could take this circle and rotate it 45 degrees and then draw that circle here. And then I do the same thing to this circle, the same thing to this circle, and the same thing to the 4th circle. Lo and behold, is that a symmetry? Yeah, it looks the same to me, right? However, I could, instead of doing everything the same to each circle, I could come here and say, I'm going to rotate this circle by 45 degrees. I'm going to rotate this circle by 180 degrees. I'm going to rotate this circle by 0 degrees. And I'm going to rotate this circle by 1.6372149863247127, the Batman symbol, pi. Okay? Clearly, even if I do it differently to each circle, it looks the same afterwards. Okay? So it is possible that you could have a local type transformation and have something be invariant under it. You had your hand up first, and then you put it down.
Does the identity of like the individual point matter? Or is it
So
just
we're going to come to that question exactly. There's a reason why I drew circles, because the one thing we know about a circle is a perfect circle is invariant under a rotation. So I intentionally did that. However, if I made special, or if I marked or identified the points along the circle, then I would be giving up this rotational invariance to start with. And we're going to formalize that observation in a few minutes. Will.
So more or less the same idea. You do have a local symmetry because of the underlying symmetry of the individual.
Sure, and I don't want us to get too carried away with these static examples. I'm just trying to give you a rough definition of these words. So the important carry away here is global and local. And eventually these are going to find their way into the vernacular of dynamical symmetries, which is going to be more important. Like I said, this is not a class on dots and circles and triangles. I would love to teach that course, but it's not going to be that. Okay, so the takeaway here is, what do we mean when we say global transformation? You do the same thing to all elements that you're transforming, or another way to say it is, at each point in space-time you do the same transformation, versus local, where you treat different elements differently, or at each point in space-time you do a different version of the transformation. And again, that will be formalized in the math later on. One thing to note, just a very quick observation, is if I have a system which is invariant under the local form of a transformation, then I'm actually guaranteed that it's invariant under the global, but not vice versa. Is there anyone that doesn't see that? If I can do a different transformation to each object and it's invariant, I'm obviously free to choose to do the same transformation to every object, and it will still be invariant. This is a stronger invariance than this. So if you're invariant under local, you're still invariant under global. But you're not guaranteed that if you're invariant under global, you will be invariant under local, as these two examples illustrate. Okay? All right. So global versus local. And again, we're going to see examples of both types of symmetries when we come to study dynamics, or dynamical symmetries later on. Then we can talk about discrete versus continuous symmetries. When we talk about discrete symmetries, there's a couple of more words that can come into play. So we can talk about finite discrete symmetries, or transformations, or we can talk about infinite discrete transformations. So let me give you examples of these. So one example, which we've already illustrated, is if I take a equilateral. I might have used the word isosceles earlier, I meant to say equilateral. If I take an equilateral triangle and I just consider rotating by 120 degrees, okay, then this transformation is discrete. Okay, you're not allowed to rotate by any angle, it has to be a multiple of 120. But if we allow ourselves to loosely remember that a rotation by 360 is, for most objects, equivalent to doing nothing, then I would really say there's only three transformations here. There's 120, 240, and 360, okay? Which is, last time I checked, a finite number. If you're in doubt, I think you can Wikipedia is 3 infinite. You might get one of those replies after they ask you to donate money. This article needs expert support for validation. 3 might be infinite, but anyway. Okay, so can anyone give me an example, perhaps, of an infinite discrete transformation?
Does an irrational number of degrees to rotate by?
A rational?
An irrational degree to rotate by through a triangle.
Are you saying irrational or
Irrational.
irrational number of degrees? Ooh. Ooh. Ooh.
Yes.
Wow, you're yeah. I like that example, but it perplexes me. I'm going to guess that that would form a discrete set that is infinite. Yeah, that gets really tricky.
Wow.
Yeah. Yeah. I'm not sure actually, because I'm not sure if, and this is where I'm going to profess to perhaps some mathematical literacy. I'm not sure if there's a notion of continuity that is associated with the irrationals. Is there any number theorists out there who can tell me whether the irrationals form not a continuous set, because they're obviously broken up by the rationals, but do the irrationals form continuous subsets of the real line? You might have just gotten yourself a homework problem. Let me give you a more concrete example, but I'll certainly look that up and report back to you next time. So a more concrete example is if we take a lattice of points that is extended to infinity along an axis. Let's call it the x-axis if you want. And we can talk about a translation of this lattice. So we could take every point on the lattice and translate it by something I call T1. That takes the whole lattice and moves it to the right 1 unit. Or I could instead take the whole lattice and shift it by a unit T2, take the whole lattice and shift it 2 to the right. The set of possible translations of the lattice Ti is infinite because it's an infinite lattice. I can shift you as many to the right or to the left as I want. But it's discrete. Okay? Is everybody comfortable with the notion of discrete versus continuous? Okay. So here's a finite discrete example. Here's an infinite discrete example. And we will encounter discrete groups, discrete transformations in the context of dynamical symmetries as well. But where we're going to spend a lot of time, and in particular the development of mathematical machinery, is our treatment of continuous transformations. And in some sense, these are, one might argue, the more important types of transformations. For continuous transformations, the notion of it being finite or infinite is not really an issue, right? Are continuous transformations going to ever be finite? No, the very notion of continuous, a continuous set, is, you can pick 2 points and there's always as many things in between those 2 points as you want. It's continuous. But there are 2 words that sort of play the same role, and that is the notion of compact versus non-compact. And so, as an example of a compact group, or a compact set of transformations, what we have in mind here is, for example, if I consider a circle, and I just think about continuous rotations of the circle, so I can rotate by any angle that I want, the idea is that the angle that I rotate by theta is allowed to take values from 0 to 2 pi, non-inclusive. So this means theta takes values on, and then this is a set, lower bound, upper bound. This means include 0, this means go up to, but don't include 2 pi. Why don't I include 2 pi?
It's the same as 0.
It's the same as 0, it'd be double counted. Okay? Now, before I use this to explain what compact means, let me just give you an example of a non-compact group, or a non-compact transformation. Still to be determined whether any of these form groups. Now we're going to take the continuous line from minus infinity to plus infinity, and I'm just going to consider translating the line by a distance d. So I'll call that transformation TD, where d takes values from minus infinity to infinity. Okay. So now, can anyone kind of put into words what the difference between compact and non-compact is?
You have a set range.
Like you just finished, that's what I was going to say.
You have like a set range of choices for compacts. Like you can only pick things between 0 and 2 pi, even though you have infinite choices. But then non-compact, you have every choice from negative infinity to infinity, which is just everything.
Yeah, if like for the second one, you could only move it from like 0 to infinity. Is that still a non-compact, or is it like a?
If you could only move it.
Or like it was like bounded by 0.
Yeah, that would be non-compact as well. It's essentially taking the interval of whatever your parameter of transformation is, and it's infinite in some direction. Okay. And these observations actually have very important consequences, and I think those of you who were in the advanced or the intermediate E&M class that I guest lectured for last semester, this distinction is actually what determines whether something is quantized in quantum mechanics. So at the end of the day, you can explain why angular momentum is always quantized in quantum mechanics, whereas translational linear momentum is sometimes quantized and sometimes not, depending on whether you've stuck your particle in a box or whether it's just on an infinite interval. Okay, so these are very important distinctions. Do you remember that, Matt?
Yeah.
Yeah, well, you did seem like it at the time. Okay. I think what's going to happen is some of you are going to decide to never take a class with me again. It's clearly when you take a class with me the second time, you are ripe for crucifixion.
Is that left bracket supposed to be inclusive or exclusive?
Sorry, on this one?
Yeah.
Well, he said, what if you're only allowed, we changed the example.
Oh, okay.
Yeah, I started out with it inclusive and then, sorry. No, I'm sorry. Yeah, so let me say another example would be this. There we go. Thank you. I was erasing half of what I wanted to change and not the whole thing. And that was okay, so any other questions about discrete? Continuous versus discrete. All right, so, and again, we're going to see examples of compact and non-compact continuous transformations. In dynamical symmetries. But 2 more words. Space-time versus internal. So one way to think about the difference between these two is that a space-time transformation, which is sometimes also called an external transformation, just to contrast it with an internal transformation. The way you can think about a space-time transformation is as follows. So if we coordinatize space-time, so that is, if in our physics theory, in our description, we decide we want to make use of some coordinates, which we usually do. If I'm talking about a transformation that affects the coordinatization, then space-time transformations generally change the coordinate system in some way. So, there are familiar examples, rotations. Okay, that's a space-time transformation. One way to think about it is if I write down a coordinate system and then I do a rotation, I can either think about passive or active. It just depends on how you want to do it. We'll fix our conventions on that in time, but if I just think about a rotation, normally I think about rotations changing coordinate systems, okay? Or Lorentz transformations, boosts, things like that. Again, to really understand the distinction here, it helps to first look at the alternative, which is what do we mean by an internal transformation? And internal transformations do not change coordinates. Now, they do in a sense, because what we're going to find in this class is that it's going to become very useful to expand our idea of space. You're used to thinking about physics taking place in space, space-time. But what we're going to do at a lot of places and a lot of points in this course is we're going to increase our notion of space to include things called isospace or internal spaces. And you can, in some sense, coordinatize those spaces, or you can at very least give them a basis of vectors. And then you can talk about rotations in those internal spaces. And the important thing is that those internal spaces, the things you do there don't touch what happens in space-time, and vice versa. When you do things in space-time, it normally doesn't impact the internal spaces. There are some very important exceptions to that, which we might or might not get to in this course. Okay? Contextually, this is, of course, where the idea of special relativity is born. Studying transformations in space-time. And the internal transformations are the types of transformations that are going to give rise to the forces in the standard model, which we also understand to be associated with gauge transformations or gauge symmetries. So we're going to see both of these throughout this course. So they're both very important ideas that we're going to get very comfortable with in due time. Okay, so now that we've got some verbiage down for transformations in general, it's time to formalize things. Okay, so this is where, hopefully, at long last, Joe Bales is going to learn group theory. And you're really not going to learn group theory from me. Well, I mean, it's the same sense in which I say this is not going to be a course in quantum field theory. You know, people take whole semesters on group theory. And still sometimes don't feel like they've learned group theory. But I want to impress on you, if nothing else, there's lots and lots, you can get very, very deep with group theory, like many things in math. But what I at least want to impress on you is that formalizing things is useful. And there was something else really important, but I forgot it. So, anyway, okay. So to formalize the language of transformations, we're going to have to introduce two important ideas from math. These are the notions of groups and representations of groups. I'm going to start by defining groups, and then we'll move into representations. You're familiar with both of these ideas, whether it's been named or not. So hopefully today we're just going to be naming it. So let me just get started with some definitions, which if you've ever seen group theory before, you've seen this definition. So a group, G, is nothing but a collection of elements. And I'm not talking about boxy cards created by Honda, of which I am a proud owner, but this is that ever so generic mathematical word that we use to refer to things that we haven't really ascribed their true identity to yet. And it's going to turn out that what the elements are of a group can be very different. Okay? So for now, I literally just want you to think that there are these things, these amorphous blobby things, and they are the elements of my group. I'm going to label them for simplicity with the letters of our favorite alphabet. And more importantly, with this collection of elements, there is a composition which I'm going to indicate by a large dot that satisfies. Now, in some texts or in some references, they'll use the word group product. I find that horribly misleading because it implies that somehow you're always going to be beating things into the form of multiplication, which is just patently wrong. Composition is a little more, I think, honest, because when we think of the word composition, what we think of is we take two things and we put them together. We compose them, and that's really what the operation does. Okay? It could be multiplication, it could be addition, okay? It could be many different things. It depends on the particular group at hand. We're going to look at a lot of examples. But what are the criterion that the composition has to satisfy? Here we go. Closure. I'm going to give each one a name, and then I'm going to give you a mathematical expression of what that is. So closure says, if I take an element A and an element B that is on the group G, then the composition of A and B is also an element of the group. Okay? Now, this is one of those things which it's almost, I don't know, this is one of those things when I first started studying group theory, I was like, of course it's on the group. Like, why wouldn't it be on the group? I just define it. A times B. It's on the group. You know, just expand my group. But that's not the way the group theory works. Okay? You don't say, oh, I'm going to have AB, and then I'm going to do A times B, and then I'm just going to make sure that that's part of my group, and I'm going to build my group. So what you normally do is you start with this set. So you don't get to just arbitrarily add shit to the set. Fix it. You start with a set, you start with an operation, and then you check the axioms. Okay? So now who, or actually just discuss among yourselves for a moment, think of a set of elements and an operation that would fail this. Go for it. Talk with each other.
2 and 3.
And let's, I heard somebody being very, well, actually, I'll just let you have that example.
Oh, right. Well, this is because see odd numbers and divisions. Odd numbers and odd integers and divisions. No, the quaternions do more complicated than they are.
Okay. This is an easy one, so I'm not going to give you too much time. So somebody give me an example of a set of elements and a composition operation that does not satisfy this. Yes?
If you have a collection of noodles and you smash spaghetti and linguine together, it's still noodles.
If you have a collection of noodles and you smash
So are they making like
noodles together, then you have what? Then you have noodles. Yes. Okay, so primes and multiplication. So if my set is all the prime numbers and my composition is just ordinary multiplication, if I take two primes and multiply them together, I no longer have a prime. Okay? Good. Now, I think numerical examples are actually a little more straightforward. You know, you can you can take odd numbers under multiplication or things like that. You know, but there's lots of ideas of if I start with the set and I'm not careful in my operation, I could easily make it so that if I combine two things, I get something that's not part of my set. Okay? So it's important because you can violate this. And if we want to make sure that what we're working with is a group, for reasons we'll talk about later on, you got to check this. So the second condition is what we call the identity. And mathematically, the identity says that there is some element, and I'm going to go ahead and call it I. There is some element which I'm just going to call I on the group G, such that the identity composed with any element A gives me back the element A for any A on the group. Okay? Now, I mean, this should be somewhat intuitive from, multiplication. The number 1 is the identity and multiplication of the real numbers. If I take any number and I multiply it by 1, I get back the number that I started with. Okay? And as long as I'm talking about the real numbers, 1 is a real number, so it's on the group. And I can do this with any number on my set. Okay? Can anybody, or actually go ahead, talk amongst yourselves, give me an example of something that doesn't have an identity. Okay, that's it. This one's pretty easy too. Can anybody give me an example? And don't give me noodles. It's going to be really hard to do noodles. Yeah, okay, so positive integers under addition. What is the identity under addition normally? It's 0, okay? But if you're only looking at positive integers, 0 is not part of the set, okay? And then there is inverse. And for inverse, we have that for any element A on the group G, there is an element which we can just call A inverse. Okay, I could call it B, but you might be, oh, why is B the inverse of A? But there's another element on the group such that A compose A inverse is the identity on the group. Okay? Can anybody give me an example of a set that doesn't have inverse? That doesn't satisfy the inverse property?
All the integers.
Under? So notice, what Matt just said was he gave me a set. He said all the integers. But that's not trying to say a group. You've got to give me a set and a transformation.
Multiplication.
So the integers under multiplication. Okay? Because remember, you might say, well, you can divide, but divide is not the operation. It's multiply. So the inverse of integer multiplication is usually non-integer multiplication, right? So multiplication by 2 has an inverse of multiplication by 1/2, but that's not in the set, all right? And notice, again, get away from always thinking in terms of multiplication because you could be talking about addition, for example, in which case the inverse works differently, the identity works differently. Notice that you kind of have to lay these out in this order because this inverse property, it makes no sense until you've introduced what we mean by an identity, because it's part of this definition. Okay, the last one is probably my favorite, and that is associativity. This one is the most mathy of all. And associativity says something like this, and this is the same associativity that you saw way back in the day when you studied the new math. I don't know if you all studied the new math. But it says if I have 3 group elements and the composition, if I compose 2 of them first and then compose the result with the third, I get the same thing if I change the order in which I'm doing that composition. And when I use the word order, you've got to be careful. I don't mean rearranging elements. That's something we'll talk about in a minute, and that's not necessarily true of a group. Here I'm just literally talking about where do I put the parentheses? Which one do I do first? Now, for us, in almost every example we look at, associativity is something that's guaranteed. We don't actually need to check it. But can anyone give me an example of something that is non-associative?
Vectors and cross products? Because you have to have that negative.
Damn it! No, no. Well, vectors and cross products by themselves?
So if I do A cross B cross C, it matters whether I do, if I can flip like A and B. Maybe that's not the same thing.
Good, I get to give you my example. This is my example. I'm so happy that I get to use my example. Because I was trying really hard to come up with a non-associative thing. So my example is this. The set is H, D, and M, and the operation is reproduction. And the issue is that H compose D is not the same as H compose D.
What are these letters?
What are these letters?
Horse, donkey, and mule.
They're horse, donkey, and mule. Because if you have a horse reproduce with a horse, you get
A horse.
horse, which you can have reproduce with a donkey to get
A mule.
a mule. But if you take a horse and a donkey and have them reproduce, you get a mule, which is not reproductive. So you then can't make it reproduce with a horse. Okay? You're all adults. I expect you to be able to digest this important piece of mathematical without snickering. Okay. All right. So, okay, so, yeah.
But in each of these
Joe,
circumstances,
we really are not going to hardball the horses, donkeys, and mules. There's more important battles for us to fight. I don't want you to chew on this too far. I really, just don't go too far away. Okay. And Jacob, actually, if I think about it hard enough, we might find something in vectors and cross products that work out. But anyway. Oh shit, I'm erasing it? Well, I'm going to erase all this. Yeah, I'm going to erase all of it because it's important for me to erase it, and yeah, that's okay. Okay, all right.
Still holds true.
So now, in all of this, I should stress that we did not require A compose B to be equal to B compose A. This property would be called commutativity, and it turns out that you don't really need to impose commutativity. In fact, a lot of the most important groups that we use in physics, the dynamical groups in particular, are non-commutative groups. All right, now we don't actually utilize the word commutativity when talking about groups, rather we talk about abelian versus non-abelian. So abelian groups are ones where you can generally commute elements, and non-abelian groups are groups where you can generally not commute elements. Sometimes, even for a non-abelian group, you can commute things. For example, the identity always commutes with everything else, or almost commutes with everything else. To be truthful, all of this you can go deeper and deeper. So for example, this guy right here, if I were being really, really super pedantic, I would define this to be what is called the left identity. And then I could separately define what is called the right identity. Okay? And there are structures, deeper in various applications of this in some aspects of physics where distinguishing these things are important and they have interesting roles. But we're not going to worry about this for most of our discussions, so we'll just have the good old identity and not worry about anything more sophisticated than this. Okay. So, one last but not unimportant observation is that if I have a group and I can take a subgroup of its elements, or sorry, I take a subset of its elements, then this guy, which I'll call H, is a subgroup of G. Now that's a very, very important formal thing. I'm not saying you can just grab a subset of these. Okay? Because you're not guaranteed that any randomly chosen subset is going to form a group. For example, if you're going to form a subgroup, what must you include in this little set? The identity. What else?
Inverse.
The inverse for each thing that you pick. Okay? So to make a subgroup, you've actually got to be a little bit careful in how you pick, and you're not always guaranteed that you can make a subgroup. Okay? All right. Where does the time go? So, all right, now is where I have to say this is going to get a little harder. Yeah.
Do subgroups have to use the same composition?
Yes. So, yeah, you're defining a completely separate and ostensibly unrelated structure if you're going to let yourself use a different composition. So the idea of subgroup is you're utilizing what's already there. You're just using a smaller set of it. So you would definitely not want to try and bring in a different composition operation. You're just restricting the number of elements to a smaller set. Okay, so far I've kind of talked about groups. We've got a formal definition of what a group is down now. And what I'm going to talk about now is probably the harder thing, and that is the notion of a representation. It is as if not more important than a group, because it turns out when we actually write down physics, we're always writing down representations of groups, not groups themselves. Okay, so when we write a Lagrangian, we actually write down the Lagrangian in terms of representations. Okay, so I haven't introduced that notion yet, but you'll see in the course of this introduction and then using this throughout the course what I mean by that. But let's see. So what I'm going to do is I'm going to so I'm going to define a group. So I'm going to define, as an example here, to work with, rotations in 2D with composition addition of angles. Okay? Now we have to be a little bit careful, and this is where I think I stumbled the most when I got into working with group theory and representation theory. In all the examples that we've been talking about so far of groups, we have looked at things like numbers and then operations combining numbers. Okay? However, what we want to talk about and use group theory and representation theory to describe are groups of transformations. So what do I mean by that? Well, an example is the group of rotations. So somebody give me an element of the group of rotations in 2 dimensions.
Identity.
The identity, great. What else?
Rotation by like 30 degrees.
Rotation by 30 degrees. Can I have another?
Rotation by 30.
Okay, yeah, all of a sudden the room lights up. I know a rotation! 62! Rotation by 666. Like 166 degrees. Okay? All right. So what's important is that these are the group elements. Not, I have a triangle, I rotate the triangle to get another triangle, that maybe looks a little different. I'm drawing the same triangle. I can't draw a different triangle. Okay, I can take a triangle and I can rotate it with these different rotations and see what I get, but these are not the group elements. These are the group elements. Okay? The group elements are the transformations. The composition is if I take 2 rotations, I create a third rotation from them by adding together the angles from each of the rotations. Okay? Now that might seem so painfully obvious that it doesn't even really merit a formal mathematical structure, but you should realize that as soon as you get into 3-dimensional rotations, that becomes a lot trickier. How do you take 2 3-dimensional rotations and combine them so that they describe a single rotation? You can do it, but it's not obvious. Like if I take a rotation around the z-axis and a rotation around the x-axis, I should be able to combine those into a single rotation around one axis. And you can do that. It's just not as intuitive as a 2-dimensional example. Okay? So here it's nice and clean. but it's generally not as obvious. But this is going to be our group for our example, and the composition is, if I take two rotations and I combine them, I just add the angle, and that's the new rotation. And now, what I want to talk about is not the group itself, but what the group acts on, i.e. the triangles. These are what we call representations, or these are going to give rise to representations of the group. Okay? Now, it's a little weird because, in some sense, representations themselves can be used to define groups. Okay? So this gets really murky, but the way that I like for you to think about it without getting too knee-deep in the really technical way of thinking about it is we're going to have groups of transformations, and then the things that you're transforming are generally representations of the group. Okay? Now these can have some very interesting properties, but one thing that I want to point out is that a single group, so one group, for example, rotations in 2 dimension, can have multiple representations and the goodest one are, if you're in a relationship, what do you think makes for a good relationship partner? They're faithful. Okay. Maybe that's not important to you younger whippersnappers. All right. So this idea of faithful representations is actually very important, because what you're going to find out is you might pick a representation, and if it's not faithful, it's not actually describing to you everything that's in the group as well as it could. So let me give you an example of what I mean by this. So I'm actually going to slightly modify the example I'm working with for purposes of this example. So let my group be rotations in a plane by 90 degrees, okay? Or multiples of 90 degrees. With the usual composition. I just add the angles to get the composed transformation if I take 2 different rotations. Okay, so I'm gonna give you a couple of examples of representations. The first one I'm going to call R1, and this representation is going to be a square, and I'm going to label the 4 corners of the square, A, B, C, D. Okay. And what I find is that this representation of this group is faithful in the following sense. If I just start with this picture, and I do nothing, I of course have that picture, but then I can do a rotation by 90, in which case I know what I get. I get A, B, C, D, which I can distinguish from the identity. So I can say, you can do this, and I can go, hey, you rotated by 90 degrees. You're cool. Like Wolfgang. Okay? Then you can, of course, compose 2 90-degree rotations to get a third element of the group, which is a 180-degree rotation. And we know that looking at the representation, now I've got A, B, C, D, which, hey, look, that's different than this and this. That's a new thing. And then finally, R270, A, B, C, D. Boom! I've got a 4-element group. And this is a faithful representation of this 4-element group. Okay? Now let's look at a slightly different representation. Levi, where are you? How many independent elements would there be in this representation of that group?
I think just two.
Just two. What would they be from up here?
The identity, the 90-degree rotation.
And the 90 degree. Okay? What we notice is that the identity comes to the identity, but so too does R180. In fact, if I gave you this and I said, I'm doing something, and I showed you the same thing, you would not be able to tell me whether I did nothing or did a 180-degree rotation, because it's not faithful. It has two levers. Okay? Here, R90 and R270 would give the same result. Okay? So do we kind of understand why at least one faithful representation is useful? Because without one faithful representation, we don't really know what all the group entails. Okay? It gets gooder. Jeff.
So what you're saying is for that representation R1 there, the group that you're using on that representation is faithful for that group. But if you use the representation R2, that is not faithful for R1's group, but it would be faithful
No.
for
So
R2.
I want to be really careful. I don't want to refer to groups by This is the group, period.
Okay.
And I'm looking at different representations of that group.
Okay, I see.
Okay?
Got it. All right.
So if this is the group, this is faithful, this is not. Don't get me wrong, I could then take this and define a two-element group for which this is faithful. But that's like, you can do that formally, I just don't want to go there.
Gotcha.
Normally we have the group and then we're just looking at different representations and asking whether they're faithful. Okay? Now who's the hoe bag? Who makes love to everybody?
No labels.
Well, yeah, I like that. I like the way I'm labeling it, and then you're like, no labels! Let's give labels to everybody! Okay? Everything is in bed with this one. Because if I label all four corners the same, how many... Maddie, where are you? Maddie? I'm not calling Maddie a hoback. Maddie, how many elements, distinct elements, are in the representation of the group in this case?
Well, you can't tell whether...
If I rotate it by 90, what does it look like? 180, what does it look like? 270, what does it look like? Exactly. Everything collapses to the identity. All right? This is useless. Not really. We'll use this a lot. This is actually called the identity representation. And it turns out that the identity representation is one representation you are always guaranteed will exist for any group. And what it means is, I'm going to take all of the group elements, and I'm going to say they do the same thing, which is nothing. And it's incredibly important that we have this option, because there are things which don't get touched by certain transformations. For example, if I do an SU3 gauge rotation, which affects the strong interactions, it doesn't touch leptons. So leptons have to be in the identity representation of SU3. Everything I just said will make a lot more sense later in the course. So I don't want you to think that this is so trivial that it's not used. It's everywhere. In fact, it's one of those things that's so much everywhere that you probably never saw it named. A lot like the number 1 or the identity matrix. Okay? If this is faithful, what do we generally call these representations? Degenerate. For the same reason we use the word degenerate in other contexts in physics. It means more than one thing kind of goes into the same pocket. Okay? All right. Okay. So, now, again, everything that I'm talking about here has been very pictorial shapes. You can think about these squares rotating. None of this really lends itself to mathematical equations. We want to do math. We want to write down equations. So we're going to have to get a language for actually describing these things mathematically, not pictorially. And fortunately, the language we're going to use to describe these static transformations is also going to lend itself when we start looking at transformations in dynamics. Okay, so the next thing that I'm going to talk about is going to show up explicitly in the same form when we talk about dynamical transformations, and this is going to be an important part of your first homework assignment. So, an important category of representations are what are called linear representations. And to get at what a linear representation is, let me just take the faithful representation from the previous example. And I'm going to look at the 4 results that I could get out of doing the group operations. So the group is the same as what I talked about before. And now what I'm going to do is I'm going to associate each of these with a column vector. Okay. And, you know, there's a certain sense in which if you think about it really hard, you might go, oh, there's like a 4-dimensional space of states, and these are the basis vectors for that 4-dimensional space of states. One axis is this axis, one axis is this axis, and then you might go, and then I do rotations in this 4-dimensional space, and then you go, wait a minute, I'm doing rotations in 2 dimensions. How the hell do I get to 4 dimensions? It's best not to think too hard about it. But we'll get into that in due time. But for now, okay, these are just labels. But what I can do, once I've set up these labels, is I can identify a corresponding matrix form for the group elements. Remember, this is representation, this is what you transform or what you act on. The group is the set of transformations. And one thing we know is that if I have a column vector and I hit it with a matrix, generally the matrix multiplies into the column vector and gives me back a column vector. It generally transformed or changed. So in fact, what you'll find is that the identity transformation is exactly what you think. It's the identity matrix. I'm not going to write in a bunch of zeros. You know what this is supposed to look like. A rotation by 90 degrees would look like this. Dying here. It's killing me. A rotation by 180 degrees will look like this. And lastly, a rotation by 270 degrees will look like this. And again, if you're trying to copy all this down, all these notes are going to be posted on the course website. So, and of course the video of this as well. Okay. Now what's really cool is that this is entirely consistent. All it relies on from you is a memory of how to do matrix multiplication, which you should all be relatively comfortable with. If you're not, go back and review it. But literally, if I take this column vector and I hit it with this matrix, I'm going to get that column vector right there, which is what I expect from this picture. Okay? But it's even cooler than that, because if I take this column vector and hit it with the same matrix, I get this one. And if I do it to this one, I get this one. Even gooder is if I take this and combine it with itself twice, I get this. 2 elements of the group combine to give me another element of the group. If I take this and combine it with this, I get exactly this. Okay? Representation, group. Now what you're going to do in the homework is you're going to look at a situation very much like this, but you're going to explore different dimensional representations. Here, I wrote a 4-dimensional representation. These things have 4 components. These are 4x4 matrices. That's kind of inspired by the fact that I have 4 labels. You know, I can kind of think of this as This, I can just think of the 1 as telling me where the A is, for example. Okay? But you're by no means restricted to a 4-dimensional representation for this group. You can look at representations in many different dimensions, and I'm going to leave it to the homework for you to explore that. The last comment I want to make, so that we can get out of here, is many of the groups that we're going to work with have these matrix representations. And the nice thing about using a matrix representation is we already have built-in composition. We just use matrix multiplication, all the rules of matrix multiplication. Okay? Really nice in that is that it's all guaranteed to be associative, because matrix multiplication itself is associative. It's not necessarily commutative. We know matrices don't have to commute when you multiply them together. Okay? Now, to finish up, and this is going to be an important thing to distinguish later on with the case of continuous groups, is with all of these different representations of the same group, we could ask ourselves, if I gave you 2 sets with a composition, is there any sense in which I could say those 2 things are the same group or different groups? Okay? And one way to do that is to construct what is called the multiplication table of the group, which is only going to work for finite discrete groups for reasons that is obvious. And a multiplication table is literally what you think of from elementary school for multiplication tables. So let me just very quickly write down the multiplication table group, or multiplication table for our earlier example, G. Okay. So I draw a grid. Across the top, I label the elements. Down the side, I label the elements. And then all I do is I go through, and in every block of the grid, I write down what I get by composing the one from here with the one from here. And if it's a non-abelian group, you have to know the order. This happens to be an abelian group, it doesn't matter, but just for the sake of argument, we'll say that you do the row first and then the column. So I would take the I from the row and compose it with the I from the column, and that gives me I. I composed with 90 gives me 90. It's the identity. It doesn't change anything. So we can fill these in pretty quickly. Okay, and then if I go down the diagonals, 90 composed with 90 is 180. 180 composed with 180 is I. 270 composed with 270 is 180. 180 and 90 is 270. 270. 180, 270. Oh, this is getting too complicated for me. And then, is that right? No, I've got to be doing this wrong. My spidey senses are tingling. 270 and 180.
290 should be 90.
Yeah, it's 90.
Yeah, that's
The other 90s you go.
These are not 90.
Those are eyes.
Yeah.
Oh, yeah, no, sorry. Yeah, sorry, that's eyes. Yeah. Okay, yeah, there we go. Okay? So this is a multiplication table for the group that we just considered, all right? My argument would be, if I could think of another 4-element group where if you wrote down its multiplication table, it had this exact same structure, it would correspond to the same group in terms of its group structure. Okay? So I think next time we meet, I'll give you an example of something which is 2 different groups, or 2 different sets of transformations which actually correspond to the same underlying group structure. But for now, I just wanted to get this idea of multiplication table out there so you can start with your homework. All right, that's it for today. We'll carry on Thursday.
All right, one.
Yes.
You've never said it.
We'll put a poster of that on.
I like that. It makes sense. Physical reason.
Did you do question 3?